All right, so here is the strobe video. It's just less than a minute. I don't think there's sound.
My job is to make college easier because
we don't need sound. And so MIT, so back in the day before slow motion footage, if you wanted to capture an image that gave us that result, you had to do something called strobe light photography. And so if you don't like strobe, close your eyes. They'll slow it down here in a second, but so it flickers every whatever time interval, okay? And so now that's a short distance, and so it's probably not every second, it's probably some semi-second. And then you superimpose, you overlay all those images together, and that's kind of hard to see, but you see the faint ball. You get the same result that we had in our picture there, okay? And so that's why you see the spacing every second. It's moving faster, faster. It's covering more ground. Now, the reason they chose a small distance does make sense, because when you have a small time frame, a small distance for the ball to travel, you can basically neglect air resistance. So hopefully last class, I told you that AP Physics makes an assumption. The assumptions are on the non-equation side of the formula chart. And assumption number 2 basically says we neglect air resistance unless otherwise stated. And so most of the problems, you don't have to worry about air resistance, drag, okay? But doesn't our life depend on drag? Ever been in an airplane? We need hot air. I've never done a hot air balloon. That would be so cool. I see them on the weekends and it's like, oh. But anyway, hot air balloons depend on air resistance. Parachutes depend on air resistance, right? And so air resistance is a good thing. It can save your life. But on the AP Physics exam, it would just complicate things, right? And so neglect it unless told otherwise. Now, what's the otherwise? You might be asked a concept question. What would, the graph look like? What would the path of the object look like if you included air resistance? So before I open the simulation, y'all tell me the picture you see on the screen right here, how would it look different if there was air resistance? Make a prediction. Not wind, don't think wind, just think air resistance. Think of air as a fluid that the object is going through. Okay. All right. So hold your hypothesis, hold your educated guess there, your prediction. Just a couple quick things. Tomorrow is the last day, quiz 1 redo. Next week starts redo for number 2. And then number 3 of 3, this is going to be your last assessment on 1D kinematics. Our next unit is going to be 2D. So I don't know if you want to consider that the 4th kinematics or the 2D assessment that we do, but tomato. But our last 1-dimension kinematics assessment, it's an exam, double column, is next week. Okay, next Wednesday, I think, is the 15th. Good deal? So we've got today all about free fall, get into some hard problems. Next class is NIMSY practice. And what's NIMSY? Well, the last few pages of your main packet looks very different. It looks more official, professional. The National Math and Science Initiative, okay? It's not from College Board, but it's created by some of the same people that write AP College Board questions. And so we really like them. We'll do as much of it as we can. Plus there's another AP style question. So that last day before exams, no new material, okay? Today there's not really new material. We've already started free fall. We're just gonna get more familiar with it, right? More practiced. Say what? And there's cliff notes, a summary, chapter, So the beginning pages of the NIMSY packet are kind of like a main points, big ideas, big reminders. And so if you turn through some of the pages, you'll see those. All right. So stop presenting. Oh, I said stop. Okay. To OneNote we go. Okay. So in our packet today, we're going to finish up page 16. We'll do some of the basic practice with freefall. And then I'm going to skip over. No, we'll do a little bit of 17. And there's our simulation. I'll come back and do that one first. And then skip over to page 19, where it's just variables, no numbers. Start getting some practice there. And then 20, we got some fun with Lex Luthor and Superman. Okay. And NIMSY starts on page 21. And so 17, I'm going to do now the link is not on your original copy. I just added it last night. If you want, you can just go to the content library and click it. But let's take a look. Oh, I forgot. You have to download the Java thing. So I've already downloaded it. And so I don't know, but it's not HTML5. A lot of physics simulations from the past were all Java based. And then apparently that's going away. And so the main ones are switching to Java HTML5. But this one, and I looked yesterday. So while my son was at gymnastics, I had my laptop and I was like, freefall simulation. And all that pulled up was like 2D. It's hard to find a 1D freefall simulation. So this is the one, oh, you can't see it. Hold on. New share. So this is the one that I decided was my favorite for a couple reasons. I have control. I can set whether I toss it up or just release it and it moves down. And the red ball, I don't know where it tells you, but the red ball has air resistance. And so we're not going to calculate with air resistance, but it's the concept. And so that was my question based on that first picture. What would it look like with air resistance? Blue, no air resistance. Red, air. Y'all ready? Play. And it plots the graph as well. And so notice it took the red ball longer, more time to hit the ground. Hopefully that makes sense. The red ball is falling through a fluid, and that's kind of weird to think about air as a fluid, but it is, right? Where blue ball is going basically through a vacuum. We neglect air resistance, okay? And so, yeah, I heard someone say they were more scrunched closer together. Red ball, yeah, every second that it collected a position, they were closer together, and it took longer for it to fall. But notice the distance of separation between the two balls, red or blue, at any 2-second intervals is different, right? And so there's not constant velocity unless you're in a parachute and you're falling at terminal velocity. Anyone know what terminal velocity is? Max speed when you're falling, okay? And why is it a max? Well, there'd be, no, it has 0 acceleration if you reach a maximum constant speed. So there you would not be accelerating, but it's when your weight is balanced by some air resistance forces. It's really a balance of forces that lead you to not accelerate anymore. Okay, and so that's the difference between air resistance and no air resistance. Good deal? All right, and then I do want to show a throw up so that you can see, not me throwing up, the ball throwing up, and so that you can see how positions, we're going to get the same thing even when you throw it up. And so reset, initial velocity, I'm going to make it positive something, okay, so that it'll be thrown upwards. Oh, it's already going. Hold on, let me reset. I'm going to make it drastic. Wait. So ignore, I'm going to bring it lower. and then throw it up. But watch the blue ball when it comes down. As it records positions, you're like, it's not recording new positions. Yeah, it is. It's right on top of the ones when it went up. And so the pattern, if all you saw was the pattern, you don't know if it's going up or down, right? You would need to know the sign of the velocity or something about time to the max peak, and then time at any other spot, and you can compare. Does that make sense? Huh? On the blue? Well, no, not the graphs. I was saying if you just saw the dots, the strobe photography dots, you don't know if it's going up or down. You would need to know either graphs or the time it took to reach the peak, and then some other time for comparison. And so, yeah, when did it turn around? The quickest way is to look at which graph. Oh, yeah, I mean, that's pretty quick. To me, there's a quicker way. The top part of the position, the max peak, right? So you can see maybe around, is it a little less than 2 seconds, maybe? Blue, looking at blue. On the velocity graph, what would you be looking for the turnaround? When it crosses zero velocity. And so where it crosses that, let me annotate here, where it crosses the zero velocity, just under 2, right? So it matches up. What about the blue line on the acceleration graph? You can't tell where it turns around. Why? Because it's the constant gravity acceleration. Look at that. They even round to -10. Now the red one looks crazy, right? Because that's not only taking into account gravity, but it's taking into account air resistance. Aren't you glad we're not going to deal a lot with air resistance? Okay. But it starts out with a huge acceleration with air resistance, because as it just begins moving, very little. But then you get more and more and more, right? And at some point it's equaling gravity, but then it tapers off to 0. So it approaches that terminal velocity. This would be the point that it enters terminal velocity when acceleration equals 0. Good deal there. Okay, so if you want to play around with this simulation, content library, just make a note to yourself on that page. I forget what page I'm on. Let's go back. I put it on page 17. So if you go to content library, but you do have to download that Java thing. So I don't know, I don't not trust it. I got it from a physics source, so I trust it, but it's up to you. All right. You know what, while we're here, let's do some concept questions. Then we'll go back to 16 and do some math, okay? And so I don't think we did this last time. Let's define what it means to be in free fall. Can someone tell me when that ball was in free fall? The moment it's released, the moment it leaves your hand or whatever object that's supporting it, it's not, here's what it's not, only on the way down. That's incorrect, okay? And so it's when the only force, and yes, I'm saying the F word, it's all intertwined, when the only force acting on the object is gravity. So we're looking not really at gravity as a force yet. It is. It's a field, it's a force, it's an acceleration. And so the force causes the acceleration. Just look at it that way. So because there's a force of gravity, gravity is going to accelerate it. And we neglect air resistance most of the time. I'd say 95% of the time. Every once in a while, there's a question, you know, what would the graph look like? What would the path look like if there was air resistance? But don't be scared. You're probably not going to be asked that acceleration graph like you saw, okay? It would probably be a simplified. You're just looking for an acceleration that reaches zero, terminal velocity. And so, number one here, concept question. A 1 kilogram box is dropped from a height of 20 meters. So 20 meters is probably the roof of this building, right? I used a motion detector the other day whenever we had them out for lab, and I just, on my table, it was facing upward. And so that distance was about 17, 18. So, you know, give another meter to the ground and then maybe another meter to the roof. So, you know, the height of this building, 20 meters. And it lands on the ground a little more than 2 seconds. If the box is filled with rocks, how long would it take to reach the ground? Y'all, small group discuss. 1 minute. I got a video to show after this. 1 minute. Talk about the answer.
The problem is like obviously they drop this rock or so I just don't know.
All right, you got your prediction? A box empty, a box filled with rocks. Now, the next time one of y'all NASA astronauts goes to the moon, I want you to take a hammer and a feather with you. I need HD video of this. I keep waiting for HD video of this, right? And so did y'all know the next person to set foot on the moon is sitting in a classroom right now?
No, I'm pretty sure that.
Could be you. That's what they say.
No, I thought they were having a launch in like 2024.
Okay, but they're sitting in a classroom somewhere maybe, right? Anyway, even astronauts got to go to school. And so y'all, this is from the 60s when they did go to the moon. And I don't know what made them think to do this, but I appreciate that they did it. They are good. And now the sound, Zoom video will have the sound, I think. But y'all are going to be listening to my computer since I'm casting. But anyway, he's going to say, I have a hammer in one hand, I have a feather in another. And thank you, Galileo, who started this thought experiment. Galileo never made it to the moon, but he thought that, neglecting air resistance, that they will land at the same time. And you're like, what? One's a feather, very, very light, low mass. One's a hammer, super duper heavy. No, they won't land at the same time, right? Is maybe what you're thinking. Well, let's see.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. And the feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here and hopefully they'll hit the ground at the same time.
Here we go.
How about that?
Okay. So hold on. I'm going to back it up. The feather's kind of hard to see. So hammer is in the astronaut's right hand. Feather, just look for a white blur, okay? A white blur, and you're kind of looking for when they hit the ground. And so I'm going to back it up one more time.
At the same time. How about that?
Okay, so the moon's gravity is about 1/6 that here on Earth, okay? So we're 9.8 technically, and I think it works out. It's like 1.6, 1.7 on the moon. So yes, there's still gravity. Objects still fall on the moon, but what's missing? Air. There's no air resistance. What would a feather do if I dropped it here today? it would kind of, air resistance is going to cause it to do this random type of path, right? It won't go straight down. And so I can't suck the air out of this room. We do have some kind of vacuum chamber, but it's not long for dropping objects. And they're not perfect. So, you know, we can't field trip to the moon, sorry. I don't think any district would allow that. I don't think I would have permission at all to do that. But hopefully you saw they did hit at the same time. So the answer to number 1 is what? Same time. And another way to confirm that, look at your kinematic equations. Where's mass? Have we calculated with mass yet? No. Okay. And true story, the mass does play a role, shape plays a role in how that air resistance comes into play. Okay, so if you move on in your physics career to calculus-based physics, you'll see that the air resistance equation does depend on shape and volume, air density, and the mass of the object. Okay, so it would be same time. No matter, a little over 2 seconds, a little more. If it was that way empty, it's that way filled with rocks. 2, a football is thrown straight up and has a velocity of 10 meters per second when it's 5 meters above the ground. What is the velocity when it is again at a height of 5 meters on the way back down? So think back to that simulation. What's the velocity when it's on the way back down? If you look at the same spot, it's the same, but negative. Velocity, the sign tells you what direction it's going. So if it's a positive velocity on the way up, when it's on the way back down, the velocity would equal negative 10. So the only difference is that sign, okay? 3, a rock is tossed up and has a velocity of 0 meters per second at the highest point. What is the acceleration at that point? So the number 1 answer, even on the AP exam, half the world answers this question. Oh, acceleration equals 0 because it came to a stop. And guess what? Half the people in the world get it wrong after a year of physics. So it's not that. Just because you come to a momentary, instantaneous stop doesn't mean you stay stopped, right? Who's still in the driver's seat? If I throw something up and it reaches a peak, who's still driving? Gravity. So the acceleration is still equal to gravity, 9.8 or 10, all that good jazz, right? Good question. So notice I did not put a negative yet. You need to define the positive direction, which this problem really hasn't, okay? So it has a magnitude of 9.8, or AP also rounds it to 10 a lot. We round it to 10 a lot. And so at this point, just want to direct your attention to our formula chart, but not the equation side. So go to the constant side. Look in the top section. They give you some known constants. Find little g. Big G we do in the spring. That's a different constant. Look at little g. AP doesn't say that it's negative. We only need to make it negative if we define up as positive. But today you'll see me do both ways. First examples on page 16, up is positive. Let's go with it, standard sign convention. But later when Lex Luthor drops Lois Lane, she only goes down. So why not make down positive, right? And so the magnitude of the acceleration is 9.8. Good deal? True or false? All objects fall at the same rate because they have the same amount of force acting on them. Now, I know we haven't talked about force, but it does depend on mass. And so technically they have different forces. That hammer and feather have a different weight force, right? They have a different weight. That's a force. but they fall at the same rate, right? The acceleration due to gravity is the same for both. And so I would say false here because of the because statement. They don't have the same amount of force acting on them, but the acceleration due to gravity is the same. So force depends on mass, but the acceleration due to gravity does not. And then 5 is going to take just a little bit longer. 5 books. So imagine this simulation, okay? 5 books are tossed or dropped from the top of a building. And here we go. Book A is thrown upward at 4 meters per second. Book B is thrown upward at 2 meters per second, half speed. Book C is dropped. Wait, they didn't give me a velocity. When you drop something, that's code. What is the velocity if you just release it? That's the acceleration, negative 9.8. What's the velocity? Not gravity. I thought we had talked about this at least once before. So it's different than a throw. Oh, day 1, we dropped a ball, right? I said, don't throw it. Try 0, right? If I just let go, it wants to stay at rest, right? Unless it's in a gravitational field that pulls it down, right? An outside force. And so note to self, dropped is a code word that 99% of the time makes it 0. I'll tell you the 1% with Lex Luthor, okay? Book D is thrown downward at 2 meters per second. So notice we've got a down 2, up 2. And book E is thrown downward at 4. So if you want a visual, we can draw out a visual here on the side. And so what you would have to assume is that they all are thrown from the same height, okay? Top of a building. So all of them start at the same initial spot. They're all going to the ground below. Yes?
Can you tell whether or not if they return the velocity or what?
No, you have to have air resistance. So a neglect air resistance unless told otherwise. So we weren't mentioned, nothing was mentioned about air resistance. And so book A is thrown upwards with an initial velocity of positive 4 meters per second. Book B is also thrown up, but half the speed. I'm going to try and draw half the size of the arrow. Initial velocity, positive 2. Positive, I'm saying up is positive, right? So gravity would be negative. Gravity pulls things down. Book C is just dropped. No arrow. So this is like our dot. No arrow is a dot. Initial velocity is 0. Book D, we throw it down at 2. So equal in magnitude, but now negative 2. And E, initial velocity is negative 4. And so the numbers are chosen on purpose, okay? Rank their speeds. Who cares about sign? Rank their speeds when they reach the ground. Who's going to hit the ground at a greater speed? Who would have a greater impact on the ground you could think of?
When they did the Spanish.
No?
No air resistance.
I can't hear you.
Yeah.
Book A. Why book A? So let's focus on book A. Let's draw kind of that strobe light, strobe photography. What happens next in the next second? What's book A gonna do? It's gonna be going upward, still at 4?
It's gonna have an acceleration.
They all have an acceleration of gravity, right? Not a constant velocity. If you have gravity, you don't have a constant velocity, right? Free fall, constant acceleration, but you can't have constant velocity. So book A, a semi-second later, yes, it's going up, but is it 4?
No.
What ish would it be? Less than 4. So it's going to go 4, 3, 2, 1. So maybe our arrows start shrinking until it reaches a max height or peak, right? And what's the velocity for that moment? 0. Just at that moment. And what goes up must come down. What's it going to look like? It's going to come down symmetric. So I'm going to kind of shift over a little bit. Maybe. Come on, pen, let me. What are you doing? Draw.
Oh, it's on this.
I know, but it was also on lasso and I didn't select lasso. No. Hold on. Can I? Okay. Maybe now it'll let me draw. So now I've come to that split second stop. Yes. Yes. I've come to that split second stop. Now I'm going to come down. I'm still accelerating the same amount. You don't accelerate more or less than the way up, right? So think back, gravity never stops. Gravity's constant for us right now, okay? In the spring, we'll talk about when gravity's not constant, but as of right now, it's constant. And so now I'm gonna speed up symmetrically in the other direction, right? And if it falls to the ground, what's that speed gonna keep doing? Increasing, right? And so this would be the final velocity or final speed that we care about. Yeah, it's negative, but speed, absolute value. What would 2 look like?
It would be like half of.
Is it going to reach the same max height? No. Right, so it's going to come right there, and then it's going to shift over. And when it reaches the height of the building, it returns to 2 meters per second, right? And it's going to keep speeding up, right? But compare that speed of impact to the book A. It'll be less. Now, let's look at E. E does not go up at all. It's already at a max height. It never has a velocity of 0. We throw it down. Gravity is going to accelerate it the same 9.8 or 10 meters per second squared. And so that -4 is going to get bigger, right? But notice A also has -4. Now my drawings weren't perfect, so work with me here, right? But it has a -4 velocity. When it returns to the building height, same position on the way down, symmetry, right? And so if they both A and E fall the same building height, yeah, the timing's different, the distance is different, but from that point, top of the building to the ground, downward direction, gravity is going to speed them up the same. So A and E hit the ground at the same speed. Different times, but same speed. Does that make sense? And so our answer to the first question, A would equal E. Tell me more. Whoa, okay.
Oh, wait, yeah.
Say again.
On your drawing thing, you put A, you have 2 arrows underneath it, but on the other.
So again, I didn't draw it perfectly. I'm only human. But so think about the A, okay? It starts +4. And then it goes up, 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 +3, +2, +1, 0. Comes back down to the building height and returns to a -4 at that building height. Well, E starts at the building height at -4, right? So it may not be identically in line because I didn't plan my drawing ahead, okay? But if they're both at the building height going -4, again, ignore time. We're just caring about what happens to the speed. And then gravity speeds them up the same amount in the same 20 meters of the building height. They're going to hit the ground with the same final speed. Okay? Different times, but same speeds.
But doesn't it matter also the distance that they
Yeah.
travel?
No, not the up stuff, because gravity slows it down, book A.
I'm not saying the other stuff.
Okay.
'Cause at that point, when it has the other stuff, it stops. That's
Mhm.
now a new down stuff.
Mhm.
So then-
But it returns to that -4. Gravity is symmetric when you return to the same position.
-4 would be the building up, 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 -4, and then down, down, down.
Yeah,
So on E, it'll be -4, down, down, down.
yes.
Okay.
The -4 down, 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 20 meters is the same for E, A and E. Okay,
No, because I'm thinking like,
Then it'll be similar for B and D.
then it'll be similar for B and D. And since they start with a slower speed, they'll end with a slower speed. And so B, but whether one's going up or down doesn't affect the impact speed as long as they fall the same distance on the building down, down, down. And then C, when you drop something, you're basically not giving it any kind of advantage, right? So it's got to speed up from rest. And so we got little arrow a little bit bigger, right? But even though it's the same height, it was given no advantage at all. So yeah, it's going to speed up, but not as much as the others. And so C is going to be the least. Rank their displacements from release to the ground. First, define displacement. Day 1, 2, change in position, be more specific. Final minus initial. Where does every ball, book, whatever it is, land?
On the ground.
So we have ground, 0 meters, minus, where do they all begin? The rooftop, 20 meters. 0 minus 20, everybody has same. Yeah, the distance that they cover is different. Who has the greatest distance? A goes the highest, max height, right? And so A will have more distance, but they all have the same displacement. Now the times are going to be different. Who's in the air longer? A. Who's in the ground? Who's in the air the least? Ooh, I hear C and E.
E, yeah.
E is correct, because remember you gave E and D an advantage compared to C. C, you're just letting gravity be the driver's seat, right? And so D and E have an advantage of being thrown. They're going to reach the ground in less time. And so A is the greatest time, E is the least. And so it just goes in sequential order. Good deal there? All right, so a lot of concepts there. We talked about, with the simulation, a little bit of air resistance. With the picture and simulation, we saw how distance every time interval gets greater and greater, right? The longer you're in the air. And then here, we got mass doesn't matter for us now. Gravity never quits. The acceleration is never 0 with free fall when you neglect air resistance, right? The only time it would reach 0 is that terminal velocity case, which is coming. There may be one question, okay? It's very rare, but most cases we neglect air resistance. And And then we see how the falling objects at different speeds and directions have different rankings. Ready for some numbers? Okay, so I see number 6 there, but I feel like I got to go back to 16. We didn't get to finish those. So it looks like we had talked about concepts. We did. I made a note to myself to talk about definition. And so we did that on page 17. By definition, free fall is not falling down. It's when the only thing acting on it is gravity. So think about it as falling up and falling down, okay? All right. So AP, even though the sheet says you can use 9.8, y'all, you can still use 10, okay? They don't want you spending a lot of test time on a calculator. They want you to be able to quickly multiply intervals of 10, okay? And so we use 10 a lot. When do you use 9.8? Labs, real life, even if we ever did an online simulation, I know that one rounded to 10, but video analysis, pivot, I don't know if y'all used those last year. You still gotta use 9.8. That's real life footage, okay? And also textbooks. You'll see textbook, whether it's their practice problems, or if you've registered for our textbook, you'll notice that I've made some optional assignments, okay? And I'll release the third one because it's going to have some free fall derived practice, but those are programmed for 9.8, okay? So if you use 10, you may get it wrong. You'll be a little bit more off, okay? But we're just doing practice here. Let's use 10. A marble is tossed up from a height of 20 meters with a velocity of 100 meters per second. What direction did we toss it? Up. I'm going to make up positive. Therefore, gravity acts negative. So I'm going to use G as negative 10. Again, AP doesn't tell me that. And by the way, AP problems don't always put let G equal 10. Okay, you can always use 9.8. You can use 10. Free response, I know you're going to show your work so the grader knows what you're doing. Hint, hint, yes? Of course. And so gravity, I'm making it 10 because we have two different up-down directions. What's the marble's velocity, sign matters, after 5 seconds? And so there is a way, you kind of intuit, you gut, you process it, you think about what's happening. Well, gravity is going to slow it down 10 meters per second every second. And since gravity is constant, in 5 seconds, it'll slow down how much? 50, negative 50, right? Decreases 50. And if you start at 100, final velocity would be a positive 50. So you can do the processing. Now, if you do this, give at least a sentence saying what you're doing, okay? Show some evidence of physics, not just a final answer. Or we can use our new derived equations. What do we know? Initial velocity, positive 100. They just told me 5 seconds. And even though they told me the initial position, you really don't need it to find the final velocity. Hint, hint, I'm going to use the equation. No position needed. Now, they did tell me acceleration, but most problems won't. Most problems, you got to ask yourself, oh, what's the acceleration? Well, it's in free fall, so it's the acceleration due to gravity. Notice I just wrote A subscript G. That's acceptable. Or you can just give it a lowercase g. That's acceptable, but do not use a capital G. That is something different, okay? And we already said we know gravity's pulling down, so we're going to make that negative 10 on this problem. This is enough to find the final velocity using which equation? The first. And so VF equals VI plus AT. Thankfully, it's already solved for final velocity. And so we have a positive 100 plus a negative 10 times 5. And notice it's the same math that we did intuitively. And we should get positive 50 meters per second. Mhm. For free fall, yeah, you're always going to use 10, assume Earth, unless told otherwise. There you go. If they take you to the moon, they'll have to tell you that one. If they take you to planet X, it's a made up planet, so they can make up a gravity. Well, but I'm meaning generic. Okay. Or Jupiter's moons or Jupiter itself. If they take you anywhere other than Earth, they'll have to tell you. Okay. They don't even make you memorize the one for Earth. It's given on the formula chart, right? You're not going to be expected to know gravity on the moon. Okay. Here's an extending question. It's not written, but let's think about it based on what we just did. How many more seconds would it take to come to that max height? 5 more seconds, because what's the velocity at the max height? 0. And to go from 50 to 0, you need to decrease 5 more seconds on top of this 5, right? So 10 total seconds to reach the max height here. Good deal? Okay. What is the greatest height that the marble reaches? And so we're looking for a final height. Now notice what I just did. I said YF. If you want to keep with X for position, you can totally do so. If you want to put H's, totally acceptable. But traditionally, as you read books, watch videos, look at review guides, traditionally with kinematics, when you're in the vertical, you switch the X to a Y. But since they said height, H is a vertical distance, right? Technically, height is just the distance between 2 points. And so it's not really a position. It's more of a scalar distance. But position, Y, is typically used for vertical positions. You don't have to keep with the X. Well, we know it starts at 20 meters, right? The ground we usually call 0. Okay. What else do we know? Well, we know it's launched upwards at positive 100 meters per second. Now pretend we don't know the time it takes to come to the max height. What else do we know? We know acceleration due to gravity is our negative 10 meters per second squared. You don't need the time. I'm going to force us to use which equation? The third. And so VF squared, I heard that. Don't scoff at the third equation. The only time the third equation is you need to slow down if you're solving for one of the velocities. Because when you square root, you got to ask yourself, is it positive or is it negative? Because the calculator isn't going to tell you. But here, that delta Y, actually, I'm going to use what's on the formula chart, YF minus Y initial. So sometimes you can write it in terms of displacement and then just solve for the final position, or you can include positions from the beginning, okay? So final velocity, I don't have that written down. What is the velocity at the max height? 0. You are not told that. That's part of free fall concepts you need to know. Initial velocity is that positive 100, even if it was negative, that's the negative you would square, right? But it's positive today, so it's nice. Plus 2 times negative 10 times that final position is what we're looking for, minus 20. And yes, the first equation would have been easier, but so we get 0 equals 100 squared is 10,000 plus, and then we've got negative 20 times, I got to distribute it to both. So I'd have a negative 20, or you can just say minus. Let's just say minus 20YF. And then negative 20 times negative 20 turns to a positive 400. Next algebraic step, combine like terms. 0 equals 10,400 minus 20YF. Next algebraic step. I would add 20YF to both sides so that everybody turns positive. And final step is divide by 20. And so 10,400 divided by 20 is going to be what? 520. And so this is your max height. The displacement traveled, if you start at 20, end at 520, displacement is start at 20 meters, go to 520, displacement would be a positive 500, right? Okay, so there's your first answer. What's the marble's acceleration at the highest point? What? Oh, you were gonna, I love it. I was gonna say 0 at first, but then I remembered half the people in the world missed that question, right? And so gravity never quits. The acceleration is not 0. Yeah, well, magnitude 10 in this problem, negative. So either way, right? But it's that 10, it's not 0. That's the main point.
If it tells you 10 in the problem and you accidentally put 9.8.
That's okay. That's okay. And really the AP reader grader point of view, if you choose 9.8, make sure you're consistent. Don't jump around within a free response problem. Oh, I feel like 9.8 on part A. Oh, I feel like 10 on part B. Don't do that unless you redefine it each time. So pick one, go with it. And those rubrics that are calculator based, they'll have both answers for the grader. You get full points no matter which one you use. All right, D, what is the velocity when it returns to where it started? Think about our books. It's negative 100, right? So the final velocity equals a negative, your initial, at the same height, right? Or same position. And so since we return back to the building at 20 meters, then our final answer is going to be negative 100. And then what's the velocity when it finally reaches the ground? So it's got to fall 20 more meters. And so there's two ways to do this. We can go very beginning to very end, or we can pick up where we just left off when we return to the building. It's the same equation. It's not, one way is not any easier than the other. What do y'all want to do? Start to finish or pick up where we left off? Pick up where we left off. So from an initial velocity, now it's an initial velocity, right? So from the top of the building on your way down to the ground, so it's all the downward direction. And so what do I know? Top of building to ground? Well, we know that your initial position is now 20 meters above the ground. Final position, the ground is 0. Y'all put those together real quick. What's the vertical displacement from the top of the building to the ground? Negative 20. You're falling down. Negative displacement. There you go. And of course, it's in free fall, so we know the acceleration due to gravity, negative 10. And so notice we don't know time. Yes, you could find it and then solve for the final velocity, or use the third equation. And so, quit shrugging. Plus 2a delta y. Now that we've already calculated the vertical displacement, I can go straight for delta y. Now solving for final velocity, here's where we got to slow down Square root, I got to think, is it positive? Is it negative? Because the calculator is going to spit out positive. And so VF squared equals a negative 100 squared, but that negative is going to go away, right? Plus 2 times negative 10 times negative 20. That negative is going to go away as well. Negative times negative. And so 100 squared is 10,000 again, plus 20 times 20. Okay. So it feels very familiar, but we're not going to subtract anything. Oop, forgot my 4. And so that's equal to VF squared. Final answer, you got to do the what? Square root both sides. And so as you pull up a calculator, it should be greater than 100, yes? We're falling down more. Should be greater than 100, so we kind of know ballpark. Those of you not calculating, should it be positive or should it be negative? Why should it be negative? It's going down, but the calculator gave you positive. We're going to round it to 102 meters per second. And so that negative sign, I had to do square root, positive or negative answer. Yes. Yeah. Okay. We're going to end Lex Luthor. Page, I forget, 20? Yeah. So we're going to do Lex Luthor. I really did want to do page 19. I highly recommend you try page 19. Go on and go there. I want you to circle the word halfway. Okay? Because later, if you're doing it right, you might be stuck and say, well, what's the distance traveled? Halfway goes for the whole page. Even though it's only written at the top, the last questions down there, it's also halfway, okay? So try this page. And again, I really wanted to do it together. I'll have a video maybe later. Every class is in a different spot. So you can check out my video for page 19 later too. But page 20, let's do Lex Luthor. By the way, you probably won't see Lex Luthor, Superman, all that kind of stuff on the AP exam. Student A, student B, whatever. I know it. We try to have fun with a PH. Fun, physics with a PH. Okay. I got to do it once. It's a corny physics joke. Okay. So page 20, here we go. With a bemused grin. Okay, who cares about that? Lex Luthor assists or drops Lois Lane off a 600-meter balcony of the Luthor Corp International Building in Metropolitan. Moral of the story, I heard 2 physics. What physics did we hear in that first sentence? Drops and 600 meters. Good. At the instant that Lois begins her plunge to a certain death, Superman begins his ascent to save her from the pavement below. So she's descending. Superman is ascending. Do you have a picture yet? So maybe we start drawing a picture. I thought of a question later I wanted to add. So that red, so I'll see it. And we'll do the whole black problem and then we'll do the red problem. How about that? But I am going to move it out of the way. So we'll do the original one first. Don't let me forget to come back. And so drawing a little picture. Here's our building. We know it's 600 meters. Now that's a height. If you want to get position technical, then the top would be y equals 600 meters. And the ground would be your 0 meter mark, right? That's tradition. Could you say the building is 0 meters and the ground is 600 meters away? If you felt like it, sure. But we got Lois Lane. No, I'm not going to try and draw her. So it's a LL box. Dropped. Initial velocity is 0. That's the code word, right? So initial velocity is dropped. And then Superman is down on the pavement below. Again, I'm not going to even try to draw Superman, but he's going to ascend from the pavement below. So she's going to fall down. Superman's going to go up. Everybody good? All right. Assume that both Lois and Superman begin at rest. So Superman, it is telling us begins at rest. And oh yeah, Lex Luthor has equipped Lois with a frictionless jumpsuit. Neglect air resistance, right? This device, okay, unencumbered by, neglect it. If Superman would happen to miss Lois on the way up, how long would Lois have to write her last news report? And at what velocity would she meet her end? So brutal, no one gets hurt in physics land, right? But in that first part, it's only Lois Lane. Superman, he doesn't catch her, so it doesn't matter. So your main object is Lois for this one. Now there's not a lot of room to show work, so I'm going to have to slide over and back, but we want the time that it takes for Lois to reach the ground below the pavement. And so for part A, we're looking for time of Lois Lane. What do we know about Lois? We said she starts at rest. What else? Right? She starts at 600 meters. She ends at 0. And so you could put those together. Her displacement, final minus initial, is negative 600. And this is all assuming down is negative, right? And speaking of down, we also, even though they didn't tell us, she's in free fall, neglect air resistance, right? Okay, so acceleration due to gravity, we're going to use negative 10. Could we have switched it around and said, well, Lois is only going down. She's going to go in the positive direction. Could we say that? If we wanted to. You'll see how the negative is going to go away. Okay. All right, is this enough? Can we solve for time without knowing the final velocity? Yeah, what equation? Number 2. And so since we already calculated the displacement, I'm going to put it in terms of delta y. Again, if you want to keep x's, that's fine. So VIT plus 1/2 AT squared. Now, luckily, VI, initial velocity, is 0. So 0 times any amount of time is 0. Note to self, if nothing zeroed out in this equation, I have t and t squared. You'd have to do quadratic. I try to stay away from that because, and AP typically doesn't ask you to use the quadratic. I mean, they give you, base times height, area of a square. Do they really expect you to memorize the quadratic equation? No, but if you know it, it could help. If you know the song, know the calculator functions. I have a program in my calculator to do it, right? But thankfully, VIT goes away, no quadratic. I can just go negative 600 equals half of negative 10. And hopefully there you see the negative goes away. Or reduces to 1, whatever you want to say. And so if we had chosen down as positive, we would have ended right here at this same place. And so half of 10 is 5, and then divide both sides by 5. So 600 divided by 5 is equal to t squared. And so what is 600 divided by 5? 120. Got to do the square root. Now, previously, I said, oh, when you square root a number, it should come out positive or negative. This is time. Do I even need to consider a negative time? No. And so t Y'all, if we pretend it's 121, we get a rounded 10.9999. So we're going to call it 11. If it makes you feel better, put 10.9. And this isn't an Earhart thing, AP, it's okay. 10.9 seconds is basically the same thing as 11. All right, so 11 seconds to her death. And then the second part of the question, B, what's the impact speed, right? Is that what it said? Velocity. So direction matters there, but impact. Now, it's not asking 10 seconds after she hits the pavement, what's her velocity? The answer is 0 probably, right? It's saying that split second right before she hits the pavement. It's the speed velocity that you hit the pavement with, okay? So it's not 0. We're going to solve for final velocity. So we can use which equation? The first one is probably the most, and I've forced us to use the third one several times. So I'll cave. Let's use the first one. We have all the same given. Yes. So since we know time, now we can plug it in. And so initial velocity zeroes out. And so we're dealing with -10 times 11 or 10.99. And so we get a negative 110. But Superman would never not catch. Oh, let's answer that question real quick. What if Lex Luthor had a jetpack and he held on to Lois? He didn't just drop her. He's got her. And he's propelling upwards, but at the end of the day, Lois still fell from Lex Luthor. Think about it for a second. What changes would we make here, if any, if Lex Luthor was going up with Lois when she fell? Small group.
So like this dropper from 600 meters still is not high with jetpack or just take off. It doesn't say.
This was a last minute add-on. I'm sorry if I didn't add every single, still neglect air resistance. We're not changing all that. Gravity same. Say again. Yeah, so it doesn't tell us how long they're accelerating. Yes, I know. It's the spirit of the question. Okay. So what changes, not every single change in the whole entire world, but in the spirit of she's not dropped, what would be different here? Distance traveled, that's a true statement. That's what I'm going for, yeah. And so, yeah, the red question. So what would be different if Lex Luthor didn't drop Lois? She was with him, they jetpacked up, her initial velocity would no longer be 0. So VI would not equal 0. What would it equal? A positive something, right? I didn't give a number, that I didn't want to get too much into it, right? But it would equal something, positive 25, positive, whenever he let go, that velocity that they were going would now be her initial velocity, right? And so it's the same thing if you're driving in a car, 60 miles an hour. Now don't litter, but what if you drop something out the window while you're moving 60 miles an hour? Well, just calm down. Okay. Yes, it's a projectile. I said the word drop, but is the initial velocity of whatever you drop going to be 0? No, it was in a car going 60 miles an hour. Initial velocity of that Coke can, whatever it is going to be 60 miles an hour. Okay. You are going 60 miles an hour when you're in a car going 60 miles an hour, right?
Are you having to find the final velocity?
No, I'm not trying to, you can do the same math here, but the biggest difference is you no longer start at 0, okay? Not yet. Okay, wait 2 weeks. Okay, so you just would put in whatever the velocity of the system, Luther and Lois, were at that moment of release, okay? And so earlier I said, when you see the word drop, 99% of the time, it means initial velocity 0. Well, that's dependent on the building or Lex Luthor not moving. But if they were moving, it'd be whatever, yeah, it'd be whatever the velocity is at the moment of release. Good deal? All right. Superman would never miss an opportunity to save Lois, right? As Lois falls, Superman accelerates upward at a rate of 50 meters per second squared to catch her. Now, I do have to address this because I know some people might critique this, so I'm going to go on and address it. It's okay. It's okay. So what do you mean? Gravity doesn't affect Superman? This is going to be a net acceleration. It's with gravity. This is Superman's final acceleration. So there you go.
Oh, if I was trying to critique the thing, it would be that it's going at right enough velocity, you can kill Lois.
Oh yeah, we won't look at the impact. So it's gonna, he timed it right. Okay, Hollywood, he timed it right.
You would actually match her downward acceleration to catch her, and then
And swoop out, yeah. Okay, but that's gonna be a net. So don't do anything with the 50. Don't add 10, subtract 10, don't do anything. That is hit. He is not in free fall. He's Superman, right? Okay. How long does it take Superman to catch Lois? And how far above the ground does it happen? Don't assume halfway unless told otherwise. Hint, hint, page 19, it says halfway. So you can do halfway. Here, don't assume 300 meters, okay? All right, and so now our picture, we've got Lois Lane. She's still gonna be dropped, go back to original. And so initial velocity 0. She'll be under the influence of gravity, negative 10 meters per second squared. And she starts at the top of the building, which is still 600 meters. She's not fallen to the ground. Somewhere, Superman's going to catch her. And so tell me more about Superman. So Superman starts on the ground. He starts from rest, they told us earlier. He's going to accelerate a positive 50 meters per second squared. And we need to know, at what time will this all happen? Well, you actually have to consider something else, okay? This is one of those problems where, oh, it would be so nice to know if we knew where he caught her, right? It feels like there's not enough given. So ish, if it's not 300-ish, towards the top of the building, towards the bottom of the building, where is he gonna catch her? Towards the top. He's got 5 times the acceleration, right? They both start at rest. He's 5 times the acceleration. And so it's probably gonna happen closer to the top. So we're gonna say this is where the final position of Lois Lane equals the final position of Superman. So this is the catch, ish. I don't really know the position, but if he catches her and pause the video, this is their final position. True story? Okay. And you have to recognize that in order to solve for time, because you got to know something about position. And so to solve for time, I'm going to slide over. And so if you start with that statement, final Lois equals final Superman, and I'm sorry, I'm going to go quick. We don't know final velocity, so I'm going to use the second equation. Now, I'm going to substitute the second equation in for both of them. And so Lois would be initial position plus initial velocity times time plus 1/2 AT squared, and this is all Lois, equals Superman initial position. Oh, VO, VI, YO, YI, same thing. Plus 1/2 AT squared. And this is all Superman. Well, Superman starts at the ground, so initial position is 0. They told us he starts from rest. VIT zeros out. Thank you very much. That made our lives easier. And so all that we need for Superman is 1/2 AT squared. Now he's not in free fall. Don't put in a -10. Lois, she starts at the top of the building, plus her initial velocity is 0 as well. This is the drop. And so that part zeroes out. And I have 1/2 GT squared. I'm doing a little bit different there because she's in free fall, he is not. Good, good. Now the time starts when she's released and Superman is Superman. He's got no reaction time. He immediately starts to accelerate. Time ends when he catches her. So these T squareds are going to be the same. That's what we're solving for. And so we get 600 plus 1/2 a -10 T squared equals, no, that was before Superman caught her. Hopefully it's less than 11 seconds because she dies at 11 seconds. 10.8 in physics land, she'd be safe. All right, so now the only variable we don't know is T squared. So if you had tried to do this with one equation, with one person, you would be stuck. You'd have 2 unknowns. This is common in AP Physics. You have to use more than one equation, right? And so I started out putting them equal. And so 1/2 of 50, 25. 1/2 of -10. And what algebra do we do next? Combine like terms, so add 5T squared to both sides. And we get 600 equals 30T squared. Almost there. I'm going fast. I'm trying to beat the bell. I'm sorry. So 600 over 30 or 60 over 3 is what? 20 and square root both sides. Give me a real answer because we're going to need it to find. So 4 point, okay, I'll go 4.47. If it's not a final answer, I try to keep as many digits as I can, but you don't need 20 digits, right? And so 3. So 4.47 seconds to catch. Now the next question, where does it happen? How far above the ground is Superman when he catches? So now that we know the time, can't we just resubstitute it into that final position equation that we have for both? Technically, if it's equal time, equal position, I can do either Lois Lane or Superman. Okay. And so what do y'all want me to do? Lois, Superman. Okay. So somebody be a rebel in the room and do Lois. I'm going to do Superman. We should get the same answer. To find the final position where he catches, I'm going to use number 2 because I don't know either of their final velocity at the catch. And so YF, oh, I said I was doing Superman, didn't I? YF, so Superman, equals Y initial plus V initial time. Those are going to zero out. Same. And so it's 1/2 of 50 times that 4.47 squared. So if we hadn't a square rooted, it'd be 25 times 20, which is 500. So of that 600-meter tall building, this is close to the top. Where's my rebel? Who did Lois? No rebels in the room? Okay. You should get 600 minus 5 times 20 minus 100, 500, okay? And then I don't think we'll have time for it, but bring back graphs. Don't forget graphs. This is not the right graph, but make rough sketches, meaning you don't have to have numbers. Put them if it makes you feel better. Position and time graph, velocity time graph, and acceleration time graph. And so position and time, velocity time, acceleration time, right? We know both of them start at 0 velocity, right? They will be opposites. And so Lois will have, what's going to happen to her velocity? Increase in the negative direction. And so I'm trying, bear with me. So there's Lois. Superman, he accelerates in the positive, and he accelerates 5 times. So it's much steeper, right? And so, woo, okay, this should be steeper than Lois. Acceleration's pretty easy. You either do the slope of the velocity, or we say, well, Lois had negative 10. So maybe I'll calm that down right there. Superman had 5 times positive acceleration. So he would be higher from the axis, right? Position is the tricky. Both are going to be curved. Lois starts where? A higher position. So Lois starts at 600. We know she's caught at 500. How am I going to connect those two? Should it get steeper or less steep? Steeper. She's speeding up. And so Lois would be, right? Superman starts at the ground, 0, and he's speeding up starting from rest. So he should get steeper as well. So it's just a sketch, not drawn to scale, but there's a qualitative sketch of both their motions. Good deal? All right, so next time, page 21 is where NIMSY starts. We're going to do a lot of those. I have one other AP level type of free response. So we probably won't make it to page 19. Give it a try. Give it a try. As well as 17 and 18 have basic to mid-level problems. To the flag of the United States of America and to the republic for which it stands, one nation,